Welcome to this lesson on one of the most fascinating phenomena in active matter physics, active colloidal Janus particles with apparent negative viscosity. First, let's understand what Janus particles are. The name comes from the Roman god Janus, who had two faces looking in opposite directions. Janus particles are colloidal particles with two distinct hemispheres that have different physical or chemical properties. One side might be catalytic, covered with platinum or gold, while the other side is inert. These particles are typically in the nanometer to micrometer size range, making them true colloidal systems. The key to their remarkable behavior is this asymmetry. The two faces give the particle a direction, a polarity that breaks the symmetry of their environment. Now the question is, how do these particles move on their own? They're not alive, they have no motors or muscles, yet they can swim through a fluid autonomously. The catalytic side of the particle converts chemical fuel molecules in the solution into products. This creates a chemical gradient around the particle. The chemical fuel could be hydrogen peroxide, hydrazine, or other reagents. The catalytic hemisphere breaks down these molecules asymmetrically. Because the reaction only happens on one side, you get an asymmetric concentration field. There are more product molecules on the catalytic side than the inert side. There are actually several mechanisms that can convert this chemical asymmetry into motion. Let me describe the main ones. The primary mechanism is called self-diffusiophoresis. The concentration gradient of products creates a slip flow along the particle surface, propelling it forward. If the reaction produces charged species, self-electrophoresis can occur. Electric fields from ion gradients drive motion. In some systems with strong reactions, bubbles form and detach, providing a kind of rocket propulsion at the microscale. These particles typically swim at speeds of 1 to 100 micrometers per second, which is quite fast relative to their size. Before we discuss negative viscosity, let's review what viscosity actually is. Viscosity measures a fluid's resistance to flow and deformation. Imagine layers of fluid sliding past each other in a shear flow. High viscosity fluids like honey resist this shearing motion strongly. Low viscosity fluids like water flow easily. The shear stress tau equals the viscosity eta times the velocity gradient. This is Newton's law of viscosity. Crucially, in all normal materials, viscosity is positive. It opposes relative motion between fluid layers and dissipates kinetic energy into heat. Now here's where things get truly remarkable. When you suspend many catalytic Janus particles in their fuel solution and measure the viscosity using embedded probe particles, something astonishing happens. Rheological measurements show that the effective viscosity can be drastically reduced compared to the pure solvent. The suspension seems to flow more easily than the liquid alone. In extreme cases, the measured viscosity can even appear negative. This means the active suspension seems to assist motion rather than resist it. You might be thinking, doesn't negative viscosity violate the second law of thermodynamics? Don't we need positive dissipation? That's an excellent question. The answer is no, there's no violation. The key is that this is an active, non-equilibrium system. Energy is continuously being injected from the chemical fuel. The microscopic viscosity of the actual liquid molecules remains positive. At the molecular level, the fluid still dissipates energy normally. The apparent negative viscosity is an effective, coarse-grained description. When you average over the active particles and their flows, the system behaves as if viscosity is reduced or negative. Let me explain the mechanism in detail. How do these swimming particles create this apparent negative viscosity? The Janus particles are constantly swimming and reorienting. As they move, each particle generates hydrodynamic flows in the surrounding fluid. Each self-propelled particle acts like a force dipole, pushing fluid backward as it swims forward. This creates long-range flow fields that extend far beyond the particle size. When you have many swimmers, their collective motion stirs the fluid continuously. This stirring injects energy from the chemical fuel into fluid motion at many length scales. The active stresses generated by the swimmers can compete with or even overcome the viscous dissipation. Instead of just losing energy to friction, the fluid gains energy from the swimmers. Let's develop a coarse-grained picture. Imagine you're a probe particle embedded in this active suspension. The probe particle experiences not only the viscous drag from the solvent, but also random forces and flows from the active swimmers passing nearby. Normally, a probe moving with velocity versus experiences a drag force F drag equals negative eta V, where eta is the solvent viscosity. But the active swimmers create additional forces. If the swimmers' collective flows tend to align with the probe's motion, they assist rather than oppose it. The total force can be written as F total equals negative eta effective times V, where eta effective is an effective viscosity. This effective viscosity is the solvent viscosity minus an active contribution. Eta effective equals Eta solvent minus Eta active. When the active contribution is positive, the effective viscosity is less than the solvent viscosity. The suspension flows more easily. If the active contribution exceeds the solvent viscosity, the effective viscosity becomes negative. Motion is actually assisted. Let's think about this more physically in terms of energy. In a normal fluid, energy is always dissipated. In a normal passive fluid, any kinetic energy you inject is constantly dissipated into heat through viscous friction. The system relaxes to equilibrium. In an active fluid, the swimmers are constantly injecting energy from the chemical fuel. This energy goes into fluid motion and stirring. If the rate of energy injection by the active swimmers exceeds the rate of viscous dissipation, the system can actually do work on a probe particle, pushing it along. Let me give you an analogy. Imagine you're trying to run through a crowded space. Scenario 1. The crowd is standing still, like molecules in a normal viscous fluid. You have to push through them, and they resist your motion. High viscosity. Scenario 2. Now imagine the crowd is moving chaotically in all directions, like active swimmers. Sometimes people bump into you and push you forward. The effective resistance is reduced. Now imagine the crowd is moving mostly in the direction you want to go, like a stampede. They carry you forward. You move faster than you could on your own. This is like negative viscosity. This isn't just theory. Experimentalists have actually measured this phenomenon in real systems. The technique is called microrheology. Researchers track the motion of small probe particles embedded in a bath of active swimmers. They measure the mean square displacement of the probes and extract an effective viscosity from how the probes diffuse and respond to applied forces. The mean square displacement equals 2 times the dimensionality times an effective diffusion coefficient times time. The effective diffusion is related to effective viscosity by D effective equals kBT divided by eta effective via a generalized Stokes-Einstein relation. In experiments with catalytic Janus particles in hydrogen peroxide, researchers have observed the effective viscosity drop by factors of 2 to 10 or even more. At sufficiently high concentrations of active swimmers, some experiments have reported apparent negative effective viscosities, where probes move faster than predicted by passive diffusion. Crucially, when the chemical fuel is removed, the particles stop swimming and the viscosity returns to the normal positive value of the solvent. This confirms the effect is due to active motion. Theorists have developed a framework to describe this using an active stress tensor. The total stress tensor sigma equals negative pressure times the identity, plus 2 eta times the strain rate, which is the viscous stress, plus an active stress contribution. The active stress is proportional to the number density n of swimmers times the average of their orientation tensor. The sign and magnitude depend on whether the swimmers are pushers or pullers. Pushers like bacteria push fluid backward and create extensional flows. Pullers like algae with frontal flagella pull fluid forward and create contractile flows. These give opposite signs of active stress. The effective viscosity can be written as eta effective equals eta minus a term proportional to swimmer density n and their persistence time tau. Higher density and longer persistence reduce effective viscosity more. Here's a question you might ask. If viscosity is negative, can we extract unlimited work and create a perpetual motion machine? The answer is no. The energy doesn't come from nowhere. It comes from the chemical fuel that powers the swimmers. The chemical fuel is being continuously consumed. To maintain the active state and the apparent negative viscosity, you must continuously supply fresh fuel. When you account for the chemical reactions and the heat released, the total entropy of the system plus the fuel reservoir still increases. The second law is satisfied. Now let's talk about applications. This phenomenon opens up exciting possibilities for microfluidic technologies. First application: ultra-efficient micromixing. Mixing at the microscale is normally very difficult because viscosity dominates and flow is laminar. By adding active Janus particles to a microchannel, you can achieve rapid mixing of reagents. The swimmers stir the fluid and homogenize concentrations much faster than passive diffusion. Experimental studies show mixing times can be reduced from minutes to just seconds by introducing catalytic nanomotors. Second application: reduced drag transport. Pumping fluids through microchannels normally requires high pressure due to viscous resistance. An active suspension with reduced effective viscosity flows more easily. You can transport the same volume with lower applied pressure, reducing energy costs. In principle, with strong enough active stirring, fluid could even flow spontaneously without any external pressure gradient, driven purely by the internal active stresses. Third application: self-fluidizing active materials. Imagine a dense suspension that can switch between solid-like and fluid-like states. Add chemical fuel and turn on the swimmers. The active stresses fluidize the material. It flows and can be shaped. Remove the fuel and it rejams into a solid. This is like a smart material that controls its own rheology. This isn't just an artificial phenomenon. Active matter effects occur naturally in biological systems. The cytoplasm of cells is full of molecular motors walking along filaments, organelles being transported, and continuous stirring by active processes. Measurements of effective viscosity inside living cells often give values lower than the same solution measured in vitro. The active processes reduce the effective resistance to motion. Suspensions of swimming bacteria like E. coli exhibit similar effects. The bacteria collectively stir the fluid and reduce the effective viscosity. Let's ask a deeper question. What physical parameters control the magnitude of the effective viscosity reduction? First, the number density of active swimmers. More swimmers produce more stirring and a larger effect. Second, the swimming speed. Faster swimmers inject energy into the fluid at a higher rate. Third, the persistence length or persistence time. Swimmers that move in straight lines for longer generate more coherent flows and stronger active stresses. Fourth, the size of the probe particle. The effective viscosity is a coarse-grained property that depends on the length scale you probe. A dimensional analysis suggests the effective viscosity goes as ETA minus a constant times N versus squared tau divided by eta. This shows the key parameter combinations. The concept of effective viscosity is inherently length scale dependent in active fluids. At the molecular scale, smaller than the size of the active particles, you always measure the normal positive microscopic viscosity of the solvent. At the mesoscale, comparable to or larger than the swimmer size, active effects emerge. This is where you see reduced or negative effective viscosity. At very large scales, the effect can either persist if there's long-range order, or average out if the swimmers are randomly oriented and create isotropic stirring. We should really think of effective viscosity as scale-dependent, ETA effective as a function of length scale R. There's also a time scale, or frequency dependence. Active fluids exhibit viscoelastic behavior. At very high frequencies, faster than the swimmers can reorient, the fluid responds like a normal passive viscous fluid. At low frequencies, where the swimmers can respond and reorient, active effects dominate and you see the reduced effective viscosity. This can be modeled as a frequency-dependent complex viscosity, with ETA effective of omega transitioning from a low-frequency value ETA 0 to a high-frequency value ETA infinity over a characteristic time tau. Despite significant progress, there are still many open questions and challenges in this field. One challenge is precisely controlling the concentration of active swimmers and their activity level in experiments. Another challenge is separating the deterministic active stress contribution from the enhanced fluctuations and noise that active particles also produce. An open question is whether stable negative effective viscosity can be maintained over large length scales and for extended times without instabilities. What are the fundamental limits? How negative can the effective viscosity get before the system becomes unstable or other effects dominate? In fact, active fluids often exhibit instabilities in spontaneous pattern formation. At sufficiently high activity, the active stresses can overcome viscous damping and lead to spontaneous large-scale flows, even without any external forcing. This is called active turbulence. Active turbulence looks like chaotic swirling flows, with vortices forming and breaking up spontaneously. It's turbulence without inertia, driven by active stresses. Various patterns can emerge: vortex lattices, mesoscale turbulent structures, or density bands. The system self-organizes due to the interplay of activity, viscosity, and hydrodynamics. These ideas connect to active liquid crystals and active pneumatics, where the particles have orientational order. In active pneumatics, you have rod-like active particles that can align with each other. Microtubule motor systems are a key example. In these systems, topological defects in the orientational field become active and can move spontaneously, powered by the active stresses. The physics is similar. Active stresses inject energy and can produce flow patterns, while viscosity and elasticity try to dissipate and resist deformation. If we want to harness these effects for practical applications, what engineering strategies should we pursue? First, optimize the particle design. Choose catalyst materials and geometric asymmetries that maximize self-propulsion speed and efficiency. Second, carefully control fuel concentration. You want enough fuel to sustain activity, but not so much that side reactions or bubble formation cause problems. Third, tune the swimmer number density. There's likely an optimal concentration that gives maximum viscosity reduction without clogging or jamming. Fourth, design the microfluidic channel or container geometry to guide and control the active flows. Boundaries and confinement can strongly affect active matter behavior. We should also consider potential issues and limitations of this approach. For biological or medical applications, catalyst materials like platinum may raise biocompatibility concerns. Alternative biocompatible catalysts are needed. In closed systems, the fuel will be consumed and depleted. You need strategies for continuous fuel delivery or regeneration. Active particles can aggregate or stick to surfaces, especially in complex fluids. Surface treatments and stabilization strategies are important. The chemical reactions release heat. In concentrated systems, you may need active cooling to prevent temperature rise and maintain control. How do catalytic Janus particles compare to other types of active matter? Living bacteria are the classic active matter system. They're more complex and exhibit chemotaxis and other responses, but harder to engineer precisely. Vibrated granular systems are another active matter platform, but they operate at much larger scales and involve inertia and collisions, quite different physics. Light-activated colloids swim in response to laser illumination. They offer precise external control, but require continuous light input. Catalytic Janus particles are autonomous, chemically powered, and highly tunable through design. They bridge synthetic and biological active matter. Looking to the future, where is this field heading? What exciting possibilities lie ahead? Imagine self-healing materials that detect damage and locally activate swimmers to fluidize the damaged region, allowing it to flow and repair it. Adaptive fluids that can switch their viscosity on command by activating or deactivating the swimmers, useful for shock absorption or flow control. Fully autonomous microfluidic lab-on-a-chip devices, where the fluid transports itself through channels without any external pumps or valves. Soft robots that use active fluids as artificial muscles, generating motion and force from chemical fuel without traditional actuators. Let's discuss the mathematical approaches used to model these systems, from microscopic simulations to continuum theories. At the microscopic level, you can simulate each individual swimmer as a self-propelled particle coupled to the fluid via the Stokes equations. The fluid satisfies the Stokes equation, eta del squared versus equals grad P, plus the force density from the particles. This is coupled to the particle motion. At the mesoscopic level, kinetic theory describes the distribution of swimmer orientations and their contribution to stress. The distribution function f of position and orientation evolves according to a kinetic equation, similar to the Boltzmann equation but with active driving terms. At the continuum level, you get modified Navier-Stokes-like equations, with active stress contributions and potentially negative effective viscosity. Let me summarize the key concepts we've covered in this lesson. Catalytic Janus particles self-propel by creating asymmetric chemical gradients around their two different hemispheres. When many such particles are present, their collective swimming continuously stirs the fluid and injects energy from the chemical fuel. The active stresses produced by the swimmers can partially cancel the viscous dissipation, leading to a drastically reduced effective viscosity. In extreme cases, the effective viscosity can appear negative, meaning the active suspension actually assists motion rather than resisting it. This does not violate thermodynamics. The microscopic viscosity remains positive. Energy comes from the fuel. The negative viscosity is a coarse-grained effective property. This phenomenon opens exciting applications in micromixing, reduced drag transport, and self-fluidizing active materials. Active matter is a beautiful example of how simple microscopic rules, each particle just swims forward, can lead to complex emergent phenomena at larger scales. It demonstrates emergence. Local activity creates collective properties that cannot be predicted from a single particle. It highlights the richness of non-equilibrium physics. Driven systems behave fundamentally differently from equilibrium systems. It's inherently interdisciplinary, drawing on physics, chemistry, biology, and engineering. Understanding active matter requires thinking across boundaries. The concept of apparent negative viscosity forces us to rethink what viscosity means in active-driven systems. Viscosity is not always just dissipation. In active systems, the interplay of driving and dissipation creates new effective material properties. The future may bring materials that dynamically control their own rheology, switching between solid and liquid, low viscosity and high viscosity, all powered by internal activity. This is a frontier area in soft matter physics and material science. We are only beginning to explore what's possible with active materials.